Hi everyone. Today, exceptionally, we are recording. We don't have a live section on the quantum hardware course because yesterday, on Friday the 8th, we had some internet issues and we could record it like a live section. So I'm recording today, and we will talk about the quantum harmonic oscillator. Let me share my screen. So, okay. And, and again, today I will talk about how to quantize the simple harmonic oscillator. This is a very important thing that we learn today because it has a lot of applications. So, but because I have too much material, so I decided like to split this presentation in two parts. So today I will show how to quantize the simple harmonic oscillator, and the next Friday we'll see how to link with the quantum information, quantum computation things. So okay, but I will start like show some slides just to give some introduction, and then I will use the whiteboard to make some calculations that we need. So okay, so again, most of the part of this lecture is based on the quantum computation, quantum information book by Nielsen and Schwann. So harmonic oscillator, we learn how to quantize it. So in this lecture, we will learn how to quantize the simple harmonic oscillator, which is a very elementary system in physics. And the formalism, as I told you in the beginning, that we learn today will be very useful to other more realistic and more physical models that we'll see in this course, quantum hardware optical models. And even would be very important when we see the other parts of the course, like when we are studying ion traps and other models. So this is a very elementary system in physics, and the formalism we learn in this example will serve as basis for studying other physical systems. So let's just give some introduction. So actually, a large number of systems are governed, at least approximately, by a simple harmonic oscillator equations. One example of this is a particle of simple harmonic oscillation is a particle in a parabolic potential well of this type. This type of potential we'll use in the example today to quantize the harmonic oscillator. But in the classical world, this could be an example like this, could be a mass on a spring which oscillates back and forth as the energy is transferred between the potential energy of the spring and the kinetic energy of the mass. It could also be present in still in the classical world in a resonant electrical circuit, where the energy is losses back and forth between the inductor and the capacitor. And in these examples, the energy of the systems is always like a continuous parameter. So today we'll see that the energy when we quantize will be not continuous, but quantizing discrete values. So in the quantum domain that we'll see today, which is reached when the coupling to the external world becomes very small, the energy of the system can only take discrete sets of values we'll see. As an example, we know that in a cavity there exists, for instance, an infinity number of possible stationary waves that in general is called like normal modes of the cavity. The electromagnetic field can be expanded in terms of these modes, and when you solve like the Maxwell equations, all each of the coefficients of these expansions obey differential equations, which is related with Maxwell equations. That is identical to uh, uh, to the equations to the simple harmonic oscillator, with angular frequency associated with each mode. So this is what we know that from the electromagnetic theory. In other words, like the electromagnetic field is formally equivalent to a set of independent harmonic oscillators. So it's important we learn how to quantize the harmonic oscillators, because still in this course we will need to quantize the electromagnetic field, and we will use a lot of the things that we learned today and in the next Friday. So the quantization of the field is obtained by quantizing these oscillators associated with the various normal modes of the cavity. And recall that it was the study of the behavior of these oscillators at thermal equilibrium, in the case of the black body radiation that we saw, I think in my first talk, basically when, like, let's say, start the quantum theory, when we were like discussing a little bit about the black body radiation, and was this type of oscillators at thermal equilibrium that led Planck to introduce the constant H that today is known as the Planck constant. So, as an example, a single mode of the electromagnetic radiation, we can give as an example a simple mode of electromagnetic radiation when it's trapped in a cavity. So the total amount of energy up to a fixed offset can only be integral multiples of h bar omega. In fact, this is the things that we'll see today. And an energy scale, which is determined by the fundamental constant h bar and the frequency of the triple radiation omega. The set of discrete energy eigenstates of the simple harmonic oscillator can be labeled by a cat like this, small n, when n can vary from 0 to infinity. And this we will see in the next Friday, which is the relationship, the things that we learned today with the quantum information. And with this relationship comes by taking a finite subset of these states to represent the qubits. And moreover, unitary transforms can be applied by simply allowing the system to evolve in time. However, we will discuss next Friday, there are problems with this scheme, and this will become clear in the next lecture. So basically, this is my slides for today, just to give some introduction. And we will begin like now to study and how to quantize the simple harmonic oscillators, and I will use the whiteboard. Okay, these are the parts how to implement quantum logic gates, such as CNOT gate. We will see only in the next Friday. So okay. So again, I'll do the same thing as in the last lecture. I will make the calculations here in the whiteboard, and then I will generate the PDF and give available. This PDF will be available for you quantum formalists. So the things I will show here, and I'll try to show you some details. They are in the box 7.2. for the new Shuang books. It's called, this box called the quantum harmonic oscillator. Okay. So let me change the color. So basically, we will consider a particle in a one-dimensional just a moment. Just a moment here. I have some problems with the. Okay, let's keep going. So consider a particle in one-dimensional parabolic potential the Hamiltonian is given by this page, p squared over 2m. This is the kinetic term plus the potential. That's 1.5 m omega squared x squared. Okay. P here is the particle momentum operator. M is the mass. X is the position operator. And omega is the frequency. Okay. So to understand this system, let's solve the Schrödinger equation. In this case, the time independent, right? Time independent part, because the potential is not time dependent. So we can solve like only can make like separation of variables, and in the end, the total, the psi, time dependent psi will need to multiply by the exponential of minus I energy in the energy. We see so this in the like in one of the previous lectures. I don't remember exactly. We read that in the end about these things. So, but now we are interested only time independent part. So this is just this derivative of psi of x plus 1 half n omega square x square psi of x equal to the energy. Okay. So here we could just simple solve this equation, differential equation, using one of the methods that we learned in the prereq material. But instead, we will use a different method here, where we would define like new operators, because this method is simple and is richer because we learn a lot of new things uh, related to the harmonic oscillator, and will be useful when we use quantize to apply to more realistic models. So the method that we will learn today will be very useful to apply to other models. So we could simple solve this. So this differential equation and find solution of psi. But instead, we will use a new method, and useful method that is simple, related, relating H, the Hamiltonian, with new operators. So since H is just this, I'll define new operators, and we will learn today the meaning of them related with this. Because remember, H is an operator, and P here is an operator, and X is operator. The momentum operator and the position operator. So because P and X are both operators, let's define. So I'll define a new operator called A, which is 2m omega h bar multiplied by m omega x plus I p. And the other, right here, a dagger, which is 1 square root 2m h bar omega m omega x is x minus IP. Okay? And you see the names for these operators. Actually, this is called the annihilation operator in this the creation operator, but we justify in the end these names. So now let's see some properties. So let's see some properties of A and A. We can use like the canonical commutation relation, like A dagger, and using this definition here, we can see, because these are just numbers like 2m omega h bar, nothing, none of them are operators. The operators here are only x and p. So we can put like numbers outside the parentheses, the commutative relation. So we will have 1 over 2m h bar omega, and the commutator of this guy and this guy. So m omega x plus IP m omega x minus I. Okay, and then can develop this to m h bar omega, and here we'll have the commutator this first with this first, so we have m squared omega squared, because they're just numbers and not operators, x plus I m omega px minus I m omega x p and plus pp. Okay. The commutator x of x is 0 because it's the same. So they commute, of course, and pp is also 0. And here, the commutator of x in p, this is just the unsustating relation, Heisenberg unsustating relation, that is just I h bar. H bar times, in fact, you should have here identity matrix, right? But I mean, we use this notation, simple notation. And this and the other px will be just the sign I h bar. In fact, I think we didn't show this. So let's just write here because this is important. This R the commutations valid at every moment of time. They say that at the same time I cannot measure with higher precision x and p. Same time, but in a different time, it's okay. And here we'll pause to give you guys some homework because I think we never prove these expressions. We just make some postulates related with them. So the proof this expression you guys can see in the Nielsen Chuan book. In fact, in other books too, but just suggesting this. You guys can see other parts if you prefer. Box 2.4, page 89. Okay, they have a more general expression than that, where they prove these commutation relations. And if you guys has any doubt, we can like discuss in another time, maybe the next Friday, okay, about this proof here. So this is a homework. This is a homework. And other homework, in the same book, the exercise 7.1, 7.2, 7.3, 7.4, and 7.5. The page, I have the page here. Wait for. Okay, using showing. So try to do this homework, and in any doubt we can in the next Friday we can discuss. In fact, most of this exercise here I will finish. I will do during my presentation. Let me just see a little bit how the recording is because I'm a little bit worried. Yeah, it's working. It's still working. Okay. Because yesterday it stopped recording and I was like speaking by myself for more than half an hour. That's okay. So today I'll just use these relations here, okay? I'll just use like the commutation relations here, and you guys try to prove these relations. So using these relations here, px is just the minus I h bar, and xp is just I h bar. So I will use this here, and I will find that a dagger is 1 to m h bar omega I m omega multiply minus I h bar minus I omega multiplied by I h bar. And this will be simple one, all the identity majors. But we'll use this notation that is simple. So, okay, this is the commutation relations of A and A dagger. We now will define a new operator I'll call N. It's defined as A dagger A. Note that n is Hermitian. This is important because the eigenvalue would be real, right? The eigenvalue is this operator. So we can see it's Hermitian because in n dagger is just a dagger a dagger. So when we have the product of two operators, we just flip. So it will be like this a and apply the dagger and a dagger dagger. So this is a dagger a, which is the definition of n. Okay. So n is Hermitian. So let's find here. Let's find a relation between n and the Hamiltonian H. First, note that. So n is just a dagger a. But if we use the definitions of a and a dagger, this will be just is 2m h bar omega m omega x minus ip multiplied by 1 to m h bar omega m omega x plus ip. So this is the a dagger and this is the a that we defined above. So we can simple expand this simple h omega, and we can like write this term multiplied by this term, m squared omega squared x squared. This term times this, and this times this, I can write in terms of the commutation relation of x and p, right, in this way. Okay, this is the middle term. This term that has px and this other px. And in the end, p squared. That's this last term. It's two last. So we can develop this, and it's easy to see that it's just h bar omega. We need to use here. Okay, let's see one more step. This is just this is IP, right? This is IH bar, sorry, IH bar. So this is 1 to MH bar omega multiply m omega omega x squared minus m omega h bar plus p squared. And we can see that is just 1 over h bar omega. So this term here, I'll put in first, p squared over 2m. Okay, so this term here is this here, and plus 1.5. I'll take in this term here now. So this will be m omega square x square minus 1/2. That is this last term here. If I divide everything by m h bar omega, in the end I'll have only this. And I separate in this way because you guys can note that this is just the Hamiltonian, the definition of the Hamiltonian. So n is h bar omega minus 1/2, or h is just h bar omega n plus. Okay. So we can denote the energy eigencat of any by the following eigenvalues. So let's denote the eigencat of any by its eigenvalue that I will call small n. Okay. So when this operator cap n is applied to the eigencat n, I will have the eigenvalue n small. Okay. Because this n is Hermitian, this must be real, right? And we'll see later show that n must be a non-negative integral. It must be real, but also must be non-negative and integral, but we'll see this in the end, not now. But for now, use the Hamiltonian on the cat n. To do that, h applied to n, we know that the Hamiltonian operator, when applied a cat, the answer is the energy cat. Okay. But we saw here this expression here, that h is related with n in this way. So h is h bar omega n plus 1/2. This is just this. And we know that, oops, when n applied to the cat and the operator n is applied to the cat n, the eigenvalue is the small n. So this will leave us with h bar omega n, because it's the result when n cap n is applied to the cat n. So this is the result. And plus 1.5. N is the energy. N. Or in other words, E, the energy, in fact, depends of N, and is H bar omega N plus 1.5. Okay? Okay. And now, to appreciate the physical significance of the operators A and A dagger, let's first note that. So let's see some important relations. For instance, the commutator of N and A, using the definition of N, this is just a dagger A, which you can write this as a dagger, commutator of A, plus a dagger A. So the commutator of this is 0, because the commutator of A with A. And this we already saw in the beginning is -1. So the result of this commutator is -A. Again, I'm not sure if in the prereq we solved in the math tools you see relations like this. But if you guys don't remember well, you can check this in the cointernology. See cointernology to see this type of relations. Okay, when you have more than one operators, more than two operators in the commutation relations. So see coin page 168. Okay. Okay, so using this, we derive. This is N, the same thing for N and a dagger. And it will be simple this dagger. And you can show that this will be a dagger. Okay. Using the same relations we use here. So using this and this as a result, we have N, a dagger N. I can write this, and using these relations we just found, I can write this as the commutator of a dagger plus a dagger N applied to N. Okay? Because the commutator here is just N, a dagger minus a dagger N, and I compensate with this plus a dagger N. So I did this because I can use this relation here. So this is simple, a dagger plus a dagger n applied to the cat n. Or just a dagger n plus a dagger n and n applied to the cat n, we'll have just a dagger plus this applied to this is just the small n by eigenvalue. A dagger n. So I can write this as 1 plus n a dagger. Okay. So this is this term. So I'll call this far because I think I need it. So in the other term is n applied to a. N. So I'll use the same thing here, the same steps I use, I'll just put the answer. The answer will be minus 1 plus n a n. And I'll call these 2 steps. So, okay, so this is just a homework. Prove this. So these relations implies these relations implies that a dagger and a at n is also an eigenvalue of my main operator n with increase or decrease, increase in this case, right, this star, or decrease in this other case, because here I have plus the unity and here minus the unity, okay, or decrease by 1. So because the increase or decrease of n by 1 amounts to the creation if it's increased, because it's plus 1 n. My state was n, but I'm summing. I'm adding one unity. So I'm creating something. In this other case, I'm annihilating something because it's n, but now it's n minus 1. So the creation or the annihilation of one quantum unity of energy h bar. So the term creation or annihilation operator for a dagger A is appropriate. We can see this not that from equation that I call two stars A and and n minus 1 are the same up to a multiplicative value. Okay, let me check again if it's everything okay with my recording. Yes. Okay. Multiplicative constant is better than value. Multiplicative constant. Constant. Because if n applied to n is just n, as we defined in the beginning, when I have something n applied for a cat, that's called n minus 1. So using a relation like this, so this should be n minus 1, n minus 1. Okay? So, on the expression we find, so from n a n, this is exactly this right side here, n minus 1 a n. So I can think comparing the last two expressions a n should be n minus 1, and you compare this, n minus 1 as a constant, and this constant will determine. Okay, so where C is a numerical constant, to be determined. And we determine by the requirement that both n and minus 1 are normalized. Normalized. Okay, so let's using this expression. So note that a and the bra of this a dagger multiplied by this guy a n is just c n minus 1 c conjugate c n minus 1. And because this is normalized, so I have c squared n minus 1 n minus 1. This is just c squared. This is 1 for the identity. Okay? And this guy here, and just the definition of n, the number operator. So this, in fact, will be n cap n equal c squared. But remember that n, the operator n applied to n, is just the small n. So this, the eigenvalue, is just n, small n, to c squared. Or n because this is my eigenvalue, n c squared. Again, this is normalized. So c is equal to square root of n. Okay. And this is by convention, okay? Because it could be plus or minus. So taking c positive by convention. And c is real because n is real, right? Because this n is Hermitian. So we obtain a n. It just remember c, the expression here. This guy here. C, but we find c is square root of n. So a applied to n is the square root of n minus 1. And similarly, it's possible to show using the same arguments as before that n a dagger n is just 1 plus n a dagger n. So A dagger and n plus 1 are the same up to a multiplicative constant to a multiplicative constant. So again, we use the same arguments that you use for A to relate A applied to the cat n would be a multiplicative constant n minus 1. We can do the same here for A dagger, the same arguments as before. So A dagger will be just C and it plus 1. And we can find the constant C using the same method. So n A dagger n will be C squared n plus 1, n plus 1, which is 1. And using the expression that we saw in the beginning, a dagger equal to 1, we can see from here that a dagger minus a dagger a equal to 1, but this is just the number operator. So a dagger is just 1 plus n. And we can use here a dagger, we can use 1 plus n. So n a dagger n is n 1 plus n, and this is just c squared. And again, this will have 1 plus, when this n operator applied to the eigencat n, this will give just the eigenvalue small n. This will be the c squared. Okay. So c, again, taking by convention only the positive part, this will have 1 plus n. And though I can use the c here, and I find a dagger n square root n plus 1 n plus 1. Okay. Okay, guys. So I think I was. No, I'll show one more thing and I will stop. Okay. So suppose that we keep on applying the operator a to both sides of the equation. The equation that we just saw. So a And this we just saw, yeah, is this. Okay, but let's apply again the same operator. So I'll apply a here in both sides. So I will have something like a squared n, and this would be just like my eigenvalue, square root of n, a applied to n minus 1. But a applied to n minus 1, according to this formula, I just need to substitute n by n minus 1. So my eigenvalue will be square root of the number I have here in my cat. So it will be square root. In this case, the number is n, but now it's n minus 1. So it's n minus 1. And the cat in the right side will be the n minus 1. In this case, a is applied here, so it will be n minus 2, because it's n minus 1 minus 1. So this is just square root of n minus 1, n minus 2. And I keep going doing this. I can do a to the cube applied to n. This would be a applied to this guy here. So I would have n minus 1 in the right side, a applied to n minus 2. And again, using this rule here, my cat instead of n is n minus 2. So the eigenvalue will be n minus 1, that is this guy here, times the eigenvalue that comes from here, that n minus 2. And n minus 2 minus 1, that is n minus 2. So okay, and I could doing this forever. But in fact, it's not forever, because I need to stop somewhere, because my oscillator, it has a ground state. It has a minimum value. So we can obtain numerical operator eigencats with smaller n until the sequence terminates. Which is bound to happen whenever we start with a positive integer n. Okay, so just one more observation. One may argue that if we start with a non-integer and the sequence will not finish. Leading leading to again cats with negative value of n. But we can avoid this using, remember, that we also have, I just have a sign here from the Google. Let me see if is everything okay. Yes. Okay, I'm just finishing. Google is asking to finish. So remember that we also have the positivity requirement for the norm of a n. Just fix this. It's ugly. The positivity requirement. So, okay. So all of this means that the norm of a n is just positive. So n a dagger applied to a n, which is the definition of norm, will be always positive. So this thing here, you give me just n a dagger a n is positive. But this is the definition of the number operator. So n n n is positive. And n applied to the eigencat n is just n. Should be bigger than 0. Which implies, so this property implies that n can never be negative. So we conclude that the sequence that the sequence should stop or must stop with n equal to 0. and the allowed values of n are non-negative. Non-negative integers. So, because the smallest value of n is 0, the ground state which is the minimum state of energy of the simple harmonic oscillator is, remember that we find in the beginning that the energy is something h bar omega n plus 1.5, but the ground state I call E0 is just h bar omega over, so this is the ground state. Ground state. Okay, so I'll stop here today, stop recording. I'll make the PDF from this slides. I'll send to you guys. And next Friday, we continue from here. We'll find the relation for the A plus operator, a Jaga operator, and then we'll find the psi that we still didn't solve the Schrödinger equation. And then we'll use the relation for the computation next Friday. So if you guys has any doubt, next Friday we can discuss. Okay. So I'll stop the presentation now. So see you guys next Friday. Okay, bye.